right, let's take a look at the notes for today. So at the top it says, remember, these are things we talked about yesterday. R sub x, that just means like the area of the region in terms of x, or like finding the area in terms of x. Alright, so the area of the region in terms of x. And this is the formula we used. Definite integral from a to b of f of x minus g of x dx. Remember, f of x, that's our top function. Right, that function has to be above g of x the whole interval. So this is our top function. Right, in this little shaded region here, it's above g of x that whole time. And g of x then is our bottom function. That has to be below the other function the whole time. And then a and b, those are the smallest x value, biggest x value for that interval. Sometimes then they give you those values. Sometimes you might have to find them where the two graphs intersect. But that's like the furthest to the left, furthest to the right. Now, we didn't really tie this into some old stuff that we did in the past, but we're going to do this today. Remember that definite integrals, when we started talking about these, before we actually got to definite integral, we were estimating area under curves using rectangles, the Riemann sums, and then we did it using more rectangles. Then we realized if we did the limit as the number of rectangles went towards infinity, we found the exact answer. Well, we're going to kind of take a step back here. We're not going to actually find the area using rectangles, but we're going to look at this visually with rectangles between these two curves. All right, so looking at this the same way we did the last chapter. So we've got basically a bunch of rectangles that are going to add up to give us this area. Obviously we can't draw the rectangles as small as we would as that number approaches infinity, but just to kind of get an idea, we're going to have these tall, skinny rectangles that as the number of those rectangles approach infinity, that's where the definite integral comes in, we get the exact area. Does anybody remember like this little measurement, like the base of these rectangles, how we represented that? Not necessarily 1/2. I mean, we had examples where it could have been 1/2, but
B minus A over N.
B minus A over N, but what was that equal to? Change in X, right? So delta X, or we also looked at it as dx. Right? Delta X, dx, those were one and the same, basically. So, like, the base of these rectangles is dx. And that's why we call this a dx cut. Because we're using, like, the dx as our base of those rectangles. All right, so a dx cut, that's used when we have vertical rectangles. And we have a top function minus a bottom function. Right? That can only work if we have that function that's above the other one the whole time. Now, if we look at the height of these rectangles, we would take this y value minus this y value. Well, this y value happens to be f of x, right? Some function of x. This y value is g of x. So this f of x minus g of x, that's basically like our height of each rectangle. This is like our base. This is our height. So we're like basically taking the base times the height of each rectangle, and then the definite integral adds all of those up. Right? It's the limit of the sum of all of those. Well, yesterday we focused on this dx cut. Today we're looking at a dy cut. Right? Where we have dy and our definite integral is in terms of y instead of x. So you'll notice we have f of y minus g of y. So everything here is going to be in terms of y. Right? These functions are going to be in terms of y. These are in terms of y. It's labeled c and d, but like we normally think of it as a and b. Those are all y values. And the difference here is we don't have a graph, a function that's above the other one the whole time. Here we have a function f of y that's to the right of this one the whole time. So we're going to have a right function and a left function. So f of y is the right function minus g of y, which is the left function. So we're doing right minus left, whereas up here we did top, minus bottom. But in both cases we're doing the bigger one minus the smaller one. Think of like on the y-axis, bigger numbers are at the top, right? So we take the top one minus the bottom one. X-axis, left and right, the bigger numbers are on the right. So the function that's on the right, that's kind of the bigger one. So we're taking right minus left. Here we have like horizontal rectangles. So here we have dy for that little change in y. And this part right here is going to be the f of y minus g of y. That gives us, whether you want to look at each one as base or height, it really doesn't matter. But those two give us that area. So a dy cut, we are using horizontal rectangles. And we're doing right minus left. Right, bigger one minus the smaller one. And then we're going from C to D, so the lowest y value to the biggest y value. So everything's in terms of y.